University, we will talk about some results on QK spaces. Please.
It's okay now? Still problem?
No problems. We see everything perfectly. You can begin.
How about now? It's okay?
Yes, everything is great. You can begin.
Okay. Thank you. Sorry for my computer. I would like to thank the organizers for this half-year online conference. Many thanks to invite me to give this talk. Today, I will talk some result on QK space. Okay. Let me first review the definition of the QK space. Let HD denotes the set of analytic functions in the unit disk D, and let DMZ be the error meter on the unit disk. Let K be a red continuous and increasing function on the interval from 0 to infinite. Analytic function f is said to be of the space QK if the superrhythm is finite in 1.1. We know that the left side of the 1.1 is not the norm. In fact, it is a similar norm. So modulus constants QK is a Banach space under the semi-norm in 1.1. For some special function K, for example, is p power p. This gives a space QP. We know that QP space was introduced by Olaskari, GHL, and Ruhan Zhao in 1995, around maybe. So it has a great development for a special function K, for example, is a constant. We get the Dirichlet space, a classical one. We know that QK space is a Mobius invariant space. It means that the semi-norm is invariant under compositing the Mobius transformation phi of the unit disk. QK space can be viewed as a space generated by a help space, dk, denoted by the QK equal to mdk, where the left side of 1.2 is also a same norm, which is a integral over unit SD. If K is a non-trivial increasing function, we know that the QK space is between the classical Dirichlet space and the below space. We know that for QP case, if P equal to 1, QP is a BMOA. If P bigger than 1, all QP are same and equal to the below space. So there are no gap between BMOA and the block space in terms of QP spaces. That is why we consider the QK spaces. For example, there are some functions K0 such that QK0 just between the BMOA and the below space. In 2004, Element and Simbertin proved that the QK space equals the Mobius invariant space generated by a weighted Bergman space L2. So we can get the 1.3, where the weight function WT is defined by K. Here we can get clearly about the W if K is given. From the 1.3, in fact, we get that F belongs to QK, even only if the symbolism in the 1.4 is finite. This is the norm of the weighted Bergman space L2. In this case, QK is between BMOA and the block space. And QK never be BMOA in this case. So BMOA is a proper subspace of QK space. We know that the logger function is very important and useful function. 1.5, the integral is finite is the sufficient and necessary condition for a logger function belonging QK space. We also know that the QK space is not separable. It has a subspace which is separable, denoted by QK naught, which is a closer of polynomials in QK space. Here, I provide 2 papers and 1 book for reference. First paper on QK space was appeared in 2000. Department of Mathematics report, Uppsala University. Later, this paper was published in the Illinois Journal of Mathematics in 2002. The co-author is Professor Mathiesen. In 2006, joined with Mathiesen and Jieshao, we published a paper several function series characterizations of Mobius invariant QK spaces. In this paper, we study systemically the weight function K, and also defined the boundary version of QK space, and also introduced the K-Carleson meter to study QK space. Several years ago, in 2017, joined with Ke Zhu, we published a book, Mobius invariant QK space. This book corrects most of interesting results on QK space, I think. Let me mention some basic properties about the weight function. We first make the following standing assumption under weighted function K. K is increasing and the rate continues. And K maps the original point to 0. And we can extend KT by K1. In fact, the QK space depends only on the behavior of increasing function K near the original point. In many situations, we need the following 2 conditions on the weight function K. We call them A and B respectively. Here, the phi k is an auxiliary function, which is defined by a supreme kst over kt. Condition A says that the integral from 0 to 1 phi k s over s is convergent. Condition B is about the integral from 1 to infinite. We find that two conditions are important to study QK space. For two conditions, I would like to mention something about them. Suppose K satisfies condition A and the doubling condition on the interval 0, 1. Then there is another weight function K1 satisfying all standing assumption such that K1 is comparable with K. And the function K1 over T power C is increasing on the interval 0, 1 for sufficiently small positive constant C. Conversely, if the function K over T power C is increasing on the interval 0, 1 for some positive C, then the weight function K satisfies condition A. It means that from if K satisfies the condition A, we can find another weight function K1 such that QK and QK1 are same. And the new weight function K1 has more good properties than original K. Suppose K satisfies condition B for some positive sigma. Then there is that a weight function K2 satisfying
Happened. I think there is some problem with internet connection. Or... Hasi, we cannot hear you. But I think you cannot hear us.
maybe Ruhan has a way to call Hasi.
Yeah.
Let me see.
One thing we can stop the recording, or at least pause the recording for now.
Okay, sorry. Let's start.
Yeah.
Yeah, everything is great.
Okay. So just I said that if K satisfies condition A, we can find another weight function K1 such that QK and Q1 are same, and K1 has more good properties than the K. Second one, if K satisfies condition B, then we can find another weight function K2 such that QK and QK2 are same, and K2 has more good properties than K. So for some special function, for example, if we choose K a power function, then we know that it satisfies A for all P and satisfies condition B for some P. We know that Carleson meter is very powerful researcher in the complex analysis, function spaces, and operator theorem, and so on. So to study the QK space, we need a similar Carleson meter. Here we call the K-Carleson meter. A positive Multiplier meter mu is said to be a K-Carleson meter if the superism is finite in the 3.1. And from the definition, it is not so clear to comparing the K-Carleson meter and the classical Carleson meter. But from the next one, this is 3.2 is a sufficient and necessary condition for K-Carleson meter. From this one, we can find some relationship between the K-Carleson meter and the classical Carleson meter. For example, if we choose K's power function K power P, then we know that the mu is the K-Carleson meter is equivalent to 1 minus z with power P. D mu is a P Carleson meter. So by using the K-Carleson meter, we can get a high order derivative characterization of QK, which can be shown in the 3.3. If here's that case satisfies condition A and B for some positive sigma, n is a positive integer. Then we have this kind of sufficient and necessary condition for QK function. If n equals 1, then we can get the definition and the K-Carleson method. Similar, by using the alpha order fractal derivative of f, we can get QK space in terms of alpha order derivative of f. This is a 3.4. Okay. In fact, we can define not only in the inside the unit desk, also outside of unit desk. Here, SG is the Carleson box for the unit desk and outside of unit desk. And 3.5, this is the definition of K-Carleson meter for both cases. Here is only different is 1 minus mod of z, which may be negative. So we use the observed here. From the following figures, we can find the little difference between them. The left side, this part is the Carleson box, and the right side of this figure, this part, dark part is outside of the unit desk for Carleson box. We use the outside K-Carleson method to investigate the relationship between QK space and the Tetramier space. In this talk, I omit this part. As an application of K-Carleson method, we can find the relationship between QK space and some kind of Moray type space. For here, we first define a new function space HK2. Let HK2 denote the space of all functions in the Hartley space H2 such that 4.1 horse, where Fi is the integral mean. I is the arc on the unit circle. Okay. Next one is some result on the relationship between QK space and Moray type space. Let K satisfy the conditions A and B for some positive sigma. If Q is sufficiently close to sigma, then from F belonging to QK space, we can find that 1 minus Q over 2 order fractal derivative of F belonging to the Moray type space. Conversely, we can get the similar result. But here, I would like to mention that the Q may be not the same, but for some special K, for example, this is a power function, the K will be same. Also, we know that in the definition of QK space, we use the derivative of F. But here we can get some derivative-free characterization of QK space. 4.2 is one sufficient and necessary result. In this result, we can find that here's only one K function of Z. In fact, in the integral, W is another variable. So we can make a little change for 4.2 to 4.3. Here we use the two functions. One is K of the Z, and here is the K of the W. We use the both variable in the double integrations. And also, if consider a Platon kernel, the d mu z, we can get another derivative-free characterization of a QK space. Next, I will mention some problem. The first one is about the BMOA. We know that for our non-trivial function K, we know the QK space is between the classical Dirichlet space and the block space. And for the, we know QK equal to classical Dirichlet space if and only if K maps the original point to positive number. And QK equals the block space if and only if the integral is finite. BMOA is a very important function space between the character space and the block space. So we hope to get some properties for K such that QK equals to BMOA. For this problem, we know that if K satisfies condition B for sigma equal 1, then QK is a subspace of BMOA. But conversely, it's not true because we can find function K such that K satisfies condition B for some sigma bigger than 1, and QK is a subspace of BMOA. For example, we can choose this kind of increasing function K. Also, we know that if K is a convex function, then QK has a subspace BMOA. And if K is concave, QK is a subspace of BMOA. for if K is concave, we have the following sufficient and necessary result for QK equal to BMOA. This is a joint result published several years ago. So the first problem is find sufficient and necessary condition on K such that QK equals BMOA. The second problem is about multiplier spaces. Let Mx be the multipliers of Banach space X. We know that modulus space of H2 is H infinite, the set of bounded analytic functions. And also for the block space, for QP space, for weighted Dirichlet space. So, how about for QK? This is our problem 2. For this problem, we have some conjecture. The models of model space of QK will be the intersection of H infinite and log QK space. Consider this conjecture. We know that if we consider the Blazik's product, this conjecture is true. So this is a result for the Blazik's product. So problem 2. So what is the multiplier space of QK spaces? Problem 3 is about the Corona Theorem. I have to go too fast. Also, I think for the Corona Theorem, several authors obtained many nice results. So here's in our result, let K satisfies A and B for sigma equals 1. The problem 3 says that how about for sigma bigger than 1? So let K satisfies A and B for some sigma bigger than 1, that the Corona theorem for multiplier space of QK still hold. The last one, the last problem is about the boundary QK space. I mentioned earlier, we can define a boundary of QK space and in this way, 4.5. And if K satisfies condition A and condition B for some for sigma equals 1, then we know the QK space and a boundary of QK space are same. I mentioned earlier, sometimes we need to consider condition B for sigma bigger than 1. So the last problem it says that let K satisfies A conditions A and B for some bigger than 1. How about the QK space and the boundary QK space? Are there same? So that's all. Thank you very much. I'm sorry for my computer problem. Thank you.
Thank you very much for wonderful talk. Any questions, comments, suggestions? Well, if not, let's thank Hasi again. And we reconvene at 9 minutes. In 9 minutes.